Welcome to section 4.4, the geometric distribution. This is our second specific discrete probability distribution that we're going to talk about in this class. All right, so let's talk about an experiment to introduce a geometric distribution. So let's suppose you want to know the probability of getting your first 3 on your 5th roll. So you're rolling a dice, you roll, and you don't get a 3 until the 5th roll. So you get not a 3, not a 3, not a 3, not a 3, and then you finally get a 3. The probability for each of the first 4 rolls to not be a 3 is 5 out of 6. So that's a probability of failure. You failed 5 out of 6 times. You didn't get that 3. The probability of getting a 3 on the 5th roll is 1 out of 6. So if we look at the probability of getting a 3 on those 5 rolls, remember these are independent. The probabilities of what you get on the first roll doesn't affect what you got in the second roll, etc. So we can multiply these probabilities together. So this is the probability of not 3 on the first roll, not 3 on the second roll, not 3 on the third roll, not 3 on the fourth roll, but finally getting a 3 on the 5th roll. Multiply those guys all together and you get about 0.0804. This is a geometric experiment. So there are 3 main characteristics of a geometric experiment. There are 1 or more trials, sort of like a binomial, but in this one is going to be failure, 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 failure until you finally succeed. In other words, you keep going until you get your first success and then you stop. So if we are throwing a dart at a bullseye, maybe we try, it takes us 6 tries to hit the bullseye. So the trials are fail, throw, fail, 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 success, and then we stop. Okay? So that's the way a geometric distribution works. A couple more characteristics. Number 2, in theory, the number of trials could go on forever. You would just keep failing. There has to be at least one, though. And the probability P of success and the probability of Q for failure need to be the same for every trial. It can't change from trial 1 to trial 2, right? They need to be the same. As always, they add up to 1 because they're complements, and Q is going to be 1 minus P. Let's do an example. We're going to play a game of chance that you either win or lose. There are no other possibilities. We're going to play that game until you win. Your probability of winning is 57% or 0.57. What is the probability that it takes 5 games until you win? And that means exactly 5 games. So that means lose, 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 win. So we're going to let X, a random variable, be the number of games you play until you win. And that's always going to be what we have X be for the geometric distribution. So this does include the winning game in our X. So X can take on the values 1, you could win the first time, 2, you could lose the first time, win the second time, 3, lose, lose, win, etc., etc. In theory, you could keep losing forever, right? The probability that X is exactly 5 is going to be a lose, 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 win, right? And that's 0.0195. We multiply all those probabilities together. And again, each trial is independent, so that's why we're able to just multiply those guys together. These are pretty easy to figure out by hand, but you can use Excel to help you figure them out. Let's talk about the notation quickly before we jump into Excel. So when we talk about the geometric distribution, instead of using a B for binomial, we use a big capital G, and that designates it's a geometric probability distribution function. And we write X twiddle G of P. P is going to be the probability of a success on every trial. Oh, wait. We're going to give this a try in Excel. So go ahead and go to MyOpenMath. Oops. And let's pull up the Excel file we need. It's under the 4.4 lecture video. So here's the Excel file we need. And open it up. Enable editing, and let's maximize this. And let's take a look at what we're doing here. We need to make this just a little bit smaller. There we go. All right, so I have quite a bit in this first spreadsheet. Let's just start at the beginning and work through it. So we're going to flip a coin until we get heads. And remember, X is going to be the number of trials until we get a success, including the success. So the number of trials until we finally get a head. So here is my X column. Here's my values of my random variable. It could be a 1, a 2, a 1, a 2, a 3, a 4, etc., all the way down. And I stop at 16, but I have should have dot, 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 right? It goes till forever. There's never going to be a stopping spot. And then what each trial looks like, I added this extra column that we normally don't have. The trial would look like I flipped a coin and got a heads. That's what the trial would be, because I'm going until I get a heads. So if I got it the very first time, I would stop. So 2 trials would look like I got a tail and then a heads, and then I stopped. 3 trials would be I got a tail, and then I finally got a head. So in this column, I have the number of fails. And we usually don't have this column, but this one's a convenient column to have. This is just equal to the number of trials minus 1, right? We're going to have 1 less failure because our last one's going to be a success. Then we have number of trials. The reason I have this is the way Excel does the geometric distribution. So here is my number of fails, and these are my probabilities for each one. And this is my probability distribution table. These are my discrete probabilities. So this is exactly 1 trial, exactly 2 trials, exactly 3 trials, all the way down. And this is my cumulative, just like with the binomial. This is less than or equal to 1 trial. Well, of course, there can only be 1. That's the minimum. So those are the same. This is 1 trial or 2 trials. This is 1, 2, or 3. Again, less than or equal to the number of trials. So this is the probability of 4 or fewer trials, all the way on up. There's 2 things we need to check for something to be a probability distribution. The first thing we have to check is that every probability is between 0 and 1, and we can see that they are. The numbers start looking a little weird down here, but remember that scientific notation. So that's like 0.000061. So that's certainly between 0 and 1. All my probabilities are between 0 and 1, and then all the probabilities should add up to 1. The trick is here, and you can see that here is we're never going to be able to check that completely because remember, in theory, this could go on forever. So these numbers as we go are going to get really, really, really small and approach probability of 0, but it's never actually going to be 0. But we could think about if we could go on for infinity, then we would have eventually get ahead. So that solves my idea about do they add up to 1. So let's try and answer these questions before I show you how to use this Excel function. So what is the probability of taking exactly 5 tries to get heads? So 5 trials means 4 failures, and that exactly is this number right here. So I'm going to write equals, and I'm just going to click on that cell because I'm lazy about typing. E9. Oh, that turned out really small. Sorry. Let's make that a little bigger. You guys can see that. And let's give that a few more decimals. Oops, that's the wrong way, isn't it? I always go the wrong way on those. All right. So what the probability of it taking exactly 5 tries to get ahead is about 0.03125. What is the probability it will take 8 or fewer tries to get ahead? So that would be 0, 1 try, 2 tries, 3 tries, up to 8 tries. All right, so we could do this by adding up all these guys, right? We could add up 0, we could add up 1 try, 2 tries, all the way including 8, because it says 8 or fewer. Or that's exactly what our cumulative distribution tells us. So we could be equals the cumulative one on 8 here. And that probability, why is this so small? I don't know. Let's fix it. So the probability of taking 8 or fewer tries is like 99.6%. If you think about it, if you flip a coin 8 times, you're probably going to get ahead in there, right? Certainly. What is the probability of getting 6 tails before getting a heads? Well, what trial would this be that we got 6 tails and then a head? Well, we would have 6 failures and then finally a success. So this is 7 trials, right? 7 trials. So that would be equal to the probability of 7 trials would be this guy right here. And I'm going to make those guys bigger, don't worry. I don't know what's going on, why this is automatically so small. I could try changing this, but as soon as I click off, maybe I'll change it. I don't know. So pretty small. Let's get a few more decimals. So the probability of getting exactly 6 tails before getting a head is a pretty small number. And what is the probability of it taking more than 3 trials? More than 3. So that would be, here's my 3 trials. I need to add everything beyond 4, 5, 6, 7, 8. Well, the trouble is we really can't add forever, although you would get close enough to that it didn't make a difference. But the way we're going to do this is we're going to use our 1 minus the probability it didn't happen trick. So this is 1, seriously, every time. That's annoying. 1 minus the probability of taking less than 3 trials. 3 trials or less, right? That's what that's going to be equal to. 1 minus the probability of 3 trials or less. So that is equal to 1 minus 3 trials or less is this cumulative one right here. That's 3 trials plus 2, this one, sorry. 3 trials plus 2 trials. Nope, I was right in the first place. I was looking at the wrong column. 3 trials plus 2 trials plus 1 trial. So that's my probability of it being 3 trials or less to get aheads. All right, now that we know how to use the probability distribution table, let's see how I came up with it. Well, Excel does not have a built-in geometric distribution. I'm not going to go too deep into this, but what they do, they call this is essentially the same thing, is a negative binom.dist. Negative binom.dist. And what it takes is, so let's go ahead and just bring it up so we can look at it, equals negative binom.dist. And it takes in the first one, it says the number of failures, and that's another reason why it's convenient to have this chart, the number of successes, the probability of a success, and whether you want it to be cumulative or not. So in our example, we're always going to have the number of successes be 1 and the number of failures be however many failures you want until you get a success. So we kind of have to think about if it's trial 1, the number of failures is going to be 0 and the number of successes is going to be 1. All right. Let's look at one of these guys. Let's look at trial 4 or trial 5 here. So we have 5 if we're looking at 5 trials, that means we have what's looking in D4. So 4 successes, 4 failures, 1 success. The probability of success is 1/2, and we're not doing our cumulative, right? So when you're thinking about the trials, you're going to break that number into the number of successes and the number of failures. And the number of successes is always going to be 1. So the number of failures is always going to be the number of trials minus 1. Let's do another example of these guys. All right. So the probability that an Oregonian is fully vaccinated against the coronavirus is 67.2% as of today. You are on campus in a classroom with 15 other people checking vaccine statuses. And we're just going to assume this is going to be an even representation of all Oregonians. X is going to be our just random variables, a number of people you have to ask before you find an unvaccinated person. So we're going to say finding an unvaccinated person is our success, air quotes, and we're going to have the probability of a success, in this case, would be 1 minus the probability of being vaccinated. So a success as probability 0.328. And we would represent this as geometric 0.328. All right, so what is the probability the fifth person you ask will be unvaccinated? So this is like, yeah, somebody vaccinated, yeah, somebody vaccinated, yeah, somebody vaccinated, yeah, somebody vaccinated, and then finally the 5th person unvaccinated. We could do this just straightforward using multiplication of independent events. 0.672 times 0.672 times 0.672 times 0.672, those are the fails, times 0.328. We can also use the built-in negative binom distribution function. So negative binom dist. It says the number of failures. Well, we want 4 failures before our 1 success. The probability of a success is 0.328. And this time we want exactly the 5th person. So we're not saying 5th or less. So it's not cumulative. So we're at the probability of exactly the 5th person we ask is unvaccinated is 0.067. Let's expand that. What is the probability we'll need to ask 5 people or less until we have a success? So this would mean we might have 1 trial, 2 trial, 3 trials, 4 trials, or 5 trials, right? So we can still use negative binom. This is a geometric distribution, but we're going to use a negative binom function in Excel. Oops, I forgot about this, didn't I? All right, the number of failures would be 4. The number of successes would be 1. The probability of success, again, is 0.328. And this time we're going to turn on the cumulative. We want to know we want to know if we had 0 failures, so that would be 1 person asked. 1 failure, that would be 2 people asked. 2 failures, you ask 3 people, etc. All the way up until we have 4 failures and the 5th person is a success. So 86.3% chance that you will need to ask 5 people or fewer until you find an unvaccinated person. All right, so what is the probability you need to ask more than 5 people? Well, that's going to be equal to 1 minus the probability that you had to ask 5 people or less. So 13.7%. And what is the mean or the expected value? We haven't talked about this at all yet, but let's think about it. 67.2%, that's about 2/3, right? So about 2/3 of the people are vaccinated. So that means at about 1 out of every 3 people are unvaccinated, right? The probability of being unvaccinated is about 1 in 3. So if we ask 3 people, right, we expect that one of them is going to be unvaccinated. So the way you compute mean for geometric is nice. The mean is equal, or the expected value is equal to 1 divided by the probability of success. So in this case, it says 1 divided by 0.328, which is about 3 people. All right, let's go back to the PowerPoint now. Let's do one more example talking about mean and a little bit about standard deviation. We're not going to be using those too much. Mean, we will. Standard deviation, not too much right now. The lifetime risk of developing pancreatic cancer is about 1 in 78. So, and that is equal to about 1.28%. Let X equal the number of people you ask until one says he or she has pancreatic cancer. Then X is a discrete random variable with a geometric distribution, right? Success would be they had the pancreatic cancer. And again, this is success in a statistical sense, not like success as we use in the English language. So success would be finally you get someone that says, yes, they've had it. So this is a discrete random variable with a geometric distribution. And we would say X is the distribution geometric with this probability of success. What is the average number of people you must ask? Again, as I told you in the Excel, and here's another note, the mean of the geometric distribution, so this is the mean, the expected value, the average number of people you should ask, right? It's going to be 1 over the probability of success. 1 over 1 in 78, 78 people. And that makes really good sense that you expect to ask 78 people before you get a success. And the standard deviation is equal to the probability of failure divided by the probability of success squared, square rooted, because we always square root for standard deviation. Plugging that in, it would be 77 in 78 over 1 in 78 squared. Plug that all into your calculator, take the square root, and you get about 77.5. Just kind of a FYI, how do you calculate standard deviation for the geometric probability distribution? All right, that's it for this one.